go back over this again. So again, 1/2 kx squared. So once I deflect that spring, that's the maximum energy that spring can have anywhere along here. That energy will be constant no matter where I am in this oscillation. Does that make sense? It will change from potential energy to kinetic energy. As I go through the middle, then all the potential energies, or go through the equilibrium point, all the potential energies turn to kinetic energy, right? Because that's my maximum velocity and acceleration has gone to 0. But anywhere in between there, I'll have a combination of potential energy and kinetic energy. But at the ends, I'll have potential energy. So the maximum energy a spring system can have is always going to be 1/2 times kx squared. Okay, now we know, and again, don't get too caught up and think all you got to memorize this because you're probably never going to use this anyway. But the x we talked about it being equal to a cosine omega t plus alpha, right? When we did with alpha being the phase constant. So you can plug that back in and get an energy equation that says this. Everybody good with that? And again, if you don't want to write this down, you don't have to. I put all this on the calendar already. All right. Now, kinetic energy is just going to be 1/2 mv squared, correct? I can go back and take what we did before and take the derivative of my position equation, which gives me the velocity. I can put that back in. So I get my kinetic energy is equal to this equation right here, which looks pretty complicated, but again, I'm going to prove it's not very hard. Does everybody see where that's all coming from? Is that okay? You see it?
Yeah.
Okay. Okay. Now, note here, if I write these all together as energy, as potential energy plus kinetic energy, I have all this, right? But now, if I take out omega here, because we know omega is the square root of k over m, right? Everybody remember that from the other day? If I put that back into this equation here, look what I end up getting. I get an equation like this. Now, if I pull out greatest common factor, which is 1/2 ka squared, I get one of my identities, right? Cosine squared of an angle plus sine squared of an angle, isn't that equal to 1? Everybody remember that?
Yeah.
So now I'm just back pretty much the same place I was. Total energy of the system is going to be 1/2 times ka squared. So again, if I deflect the spring 10 centimeters, then 1/2 times the spring constant times my amplitude, which would be 0.10 squared, would give me the maximum energy that that system can have. And that energy is constant anywhere in that oscillation. So even though these equations are shown, the only one you really need to remember is this. That's your energy equation first. Right good with that? Okay. Now, if you want to find the velocity at any point and you don't want to go back and use the time equation, I've done this, I've derived this, but you can go back and say the velocity at any point is going to be plus or minus omega times the square root of my amplitude squared minus my x squared, where x is the distance from the equilibrium point. So I can use this equation here to find my velocity no matter what.
So this equation was on the sheet?
This equation, I would write this equation down. I can't remember if they put that on the AP exam or not. But I'm going to make sure you guys have it available when I get ready to take it, whether we have to put it in the calculator or what.
Just a little bit.
What's that?
Sorry.
Oh, sorry.
Thank you.
Okay, so the value of knowing this equation here is if I know my velocity at any deflection, then I can find my kinetic energy, correct? Right, and go back to 1/2 mv squared. So if I know the total energy in my system, and the question says, what's my potential energy when x is 2 centimeters? Then I can go back and say, I can put in my amplitude, I can put in this as 0.02, I can find my velocity, I can find my kinetic energy when I'm at 2, I can subtract that from my total energy to get my potential energy. Does everybody understand what I'm saying there? Okay. Let me draw it up here to see if it makes sense. If I have a spring, I'll draw this. I'll do a vertical spring where I have no deflection or no friction. And I have a mass here. I'll move it a little closer. Then I'll draw a spring here. Okay. Now if I pull this guy back to here, and I've deflected this spring, then here, let's say this amplitude is, I'll keep something simple. Let's say it's 2 meters, which is very extreme, right? So when my amplitude, if I pull it back and let go of it, my amplitude here is 2 meters. Everybody agree with that? So when my total potential energy, or total energy the spring could have, my potential here would just be 1/2 times k times a squared. That would be the total energy that spring would have. Does everybody see that? In this case, I would put in my k value, and let's just I'll make something up. Let's say k is 1,000 newtons per meter. So my total energy would be 1,000 times 2 squared. That's the total energy that spring's going to have anywhere, whether I'm pulled back here at the end and let it go, or it goes through the equilibrium. That's the total energy that spring can have. Does everybody understand that? Now, if say I want to find out, well, what's the potential energy going to be when I get right here, and what's the kinetic energy going to be right there? Well, I could use this equation right here and find out what the velocity is when it goes back through that point, correct? If I knew my velocity through that point, I could find my kinetic energy, because I know my kinetic energy is going to equal to 1/2 times mass times velocity squared. So if I had my kinetic energy, all I have to do is subtract it from this potential energy, or total energy. That's how much potential energy I'd have at that point. Because the potential energy and the kinetic energy added together must equal this at all points in time. U may just potential energy. You can make it total in this case, because that is all it has. When I pull it back, all the potential is also equal to the total energy of the system. Yes?
But when that goes to the top of the equation, will that be adjacent to you, or
no, you may have to give it. But remember, omega is going to equal nothing more than the square root of k over m. So if you know the spring constant, you know the mass, you can always find omega. So does that make sense to everybody? It should be. I hope that's fairly comfortable. So the ones you really, again, the equations you're pretty much going to need to know to do all the energy is going to be this one here and this one here. Those two equations right there are going to let you find the energy of any spring system.
So to read this one's where you substituted distance of
You don't need those. No. That's what I'm saying. That yeah, you can do all that, but it all ends up back to this point anyway. Okay, comfort level good with that? Okay. All right. So let's try like a problem like this. If you guys want to try this one on your own, I think you can do it. You have a 0.5 kilogram cart connected to a light spring in which the force constant is 20 newtons per meter. Calculate the total energy of the system, the maximum speed if the amplitude is 3 centimeters. If you can't work it, then I'll help you work it, but I think you could do it. And you guys remember this too, right? V max, which is always be omega times A. And acceleration max will always be omega squared times A. Let me just see if I worked this one. I don't remember if I did or not. No, I did not. Did everybody get 90 joules for total energy? Okay.
Wait, stop.
Mm-hmm.
Shouldn't it be 0.009 joules? Because that's what I got. Because amplitude is given in centimeters.
Oh, I'm sorry. I'm sorry. My fault. No, my fault.
Just give us per meter.
Thank you very much. What'd you get? Point what?
0.009 joules.
Okay, and then maximum speed. Everybody understand how to get your omega, right? Or not? So again, to get it, I'll do it here. Omega is going to equal the square root of k divided by mass. So 20. Make sure my units are good. Over 0.5. That gives you what? Square root of 40. So if you want to find V max, now you can leave this in centimeters if you want. Just get it in centimeters per second. It doesn't matter. So my velocity max would equal to the square root of 40 times 3, and then my units would be in centimeters per second. Then when my acceleration max would be 40 times 3, which give me 120 centimeters per second squared.
So why is it that omega is equal to the square root of k, right?
It is for spring constants. In the last lecture, I think.
Oh.
Yeah, just in the last lecture, I know I defined it that way.
Oh.
If you want to do pendulums, it'll be the square root of L over G, too. And we'll cover that some more before the AP exam too. Because I think I got one day scheduled during the review to spend strictly on gravitation. And does everyone understand how to find the velocity of the cart when you're at 2? Right, to do that, you're just going to go back and use this equation right here. And does anyone have that value for the velocity at 2 or not? What you got?
1414.
Say that again now.
0.1414.
0.1414. And you did, is that meters per second? Okay. And then what did you get for kinetic energy here? Did you get that? 0.005 joules. And what did you get for potential energy there? Okay. And you notice, again, they got to add up to be that.
And that in centimeters.
Which one's that? This one will be in meters per second. I mean, you can do it in centimeters per second. Nothing says you can't. Okay, everybody, are we good with this? Questions? Uh-huh.
For the kinetic energy, do you have to figure out the time in order to get that? Or
Do you have to do kinetic energy to define it?
do you have to find the time for the kinetic energy?
No, you don't have to, because what you could do would be, if you go back to this equation here, you can find the velocity at any deflection, right? And then you can just do 1/2 mv squared.
Okay.
How do we do the potential energy for that?
Well, you could have done, one thing you do is just do 1/2 kx squared, because the potential energy on a spring at any point in time is going to be 1/2 times k times the kx squared. That's going to tell you the potential energy at any point away from equilibrium. And if you did that, that should have given you a 0.004. You didn't get that? You got that? Okay. So again, I hope you find this fairly logical. Okay. Let's see here. I'm not going to make you work a bunch of problems. And you guys want to try another one, or do you feel comfortable with that? I just want to get you back to the web of study as fast as possible if I can. Alright, let's see if there's anything else. I'm going to skip through this law of this because some of this is just repetition. Pendulums, I think what I'm going to do on pendulums is I'm going to wait and do those when we do the review for AP. I'm going to just be honest with you, the only difference between pendulums is the omega here is going to be the square root of L over G. That's going to be the only major, or where you have this value here, then we can substitute back in and we get, actually I want to do this, omega is going to equal to the square root, I think it's G over L, right? And again, we'll come back to that when we do the review. I'm not going to have pendulums on the test tomorrow. Okay. The other thing that might be thrown at you again, and we'll review it prior to the AP exam, and I don't think they're going to give it to you. If they give you a physical pendulum, they're going to have to give you this equation for the period. And all it's going to be here is if you what a physical pendulum is some object where you're rotating around some point that's not the equilibrium point. And that's just going to be 2 pi times the moment inertia of this around this point here, divided by the mass, divided by G, divided by D. And D is going to be the distance from here to the center of mass.
So you need to find the center of mass.
Yeah, I think when I went back and looked through old AP exams when they'd done that, I think that I found one instance when they had a problem like this, but they gave you this equation for period, so it wasn't really that difficult to do. And I think they gave you the inertia. They didn't make you go through and calculate inertia and all that. Right? And the only other one that I've seen one other time is for torsional pendulums. And torsional pendulum is something that you rotate, and then when you let it go, it just does this back and forth like this. Rotates around, and the period here is going to be 2 pi times the square root of moment inertia divided by k. They would have to, yeah, they'd have to give you k. So I mean, I wouldn't get too uptight about this right now. When we start doing the review, I'll try to find a problem like they've done in the past. I'll show you an example of that. Okay, questions? I know it's a fairly quick lecture, but the main thing is how to do the energy of these systems.
And the pendulum stuff?
What's that?
Is the pendulum stuff all over?
No, there's no pendulum on the homework at all. No. Okay, you guys want to take about 40 minutes and try to knock this out, and then we'll get to the review?